First of all, hi to everybody, and thanks a lot to Tunkai for the very nice invitation. So the workshop looks really interesting, and as he commented, I quite focus on the same aspects as the workshop. So it's great to be here. I would have preferred to be physically in Ankara with the rest of participants, but knowing that the situations we're having these 2 years, it's almost impossible to think in that right now. And well, I'm also glad to share keynotes with people like Javier with a very interesting talk. Also because what I'm going to present is very much in the line of what he has presented. So what I have prepared, it's a mix of 2 or 3 different works that have the common aspect of using FFT homogenization to model size effects in the deformation of metals, both at the micro and the mesoscale. So the work has been performed with the collaboration of 3 persons mainly. One is Sergio Lucarini, that is a former PhD student that now will start a postdoc with Emilio Martinez Pañeda, another of the keynote speakers in the UK. Okay, Marco Magri is a postdoc that he has just finished with me, and Sarah Halola, that she was a postdoc working with Javier Segurado and myself the last 2 years. Okay, so I will make a motivation of this problem. I will show the FFT homogenization framework without too many details, but just showing which are the principal statements and the principal equations, and then I will present the 2 works. So at the micro scale, I will show how we develop a model to take into account grain size effect in the mechanical response of polycrystals, okay, in this case through strain gradient crystal plasticity. And the second example is we go to a larger length scale where we don't see the grains, okay, but we still have some particle, some size effects. In this case, it's the size of the particles that introduce a size effect, but in this case, we are not only focused on the strength, but also on the damage, and I will show some conclusions. So with this, I cover 2 aspects of the workshops that are even in the title, that is plasticity and damage in metallic materials. Okay, so let me just minimize this. So it is very well known, okay, that the microstructure plays a fundamental role in the mechanical behavior of materials, but the word microstructure can refer to very different things in very different length scales. So we can go at the nanoscale, so behind the grains, and there is a strong effect on the macroscopic response on things that happens on this scale. For example, dislocation density, the presence of sub-nanometric precipitates, the composition of the crystal due to things like solid solution, etc. We have another scale where we can define another particular microstructure. This is the microscale, okay, and in the microscale, the microstructure can be defined. We don't see dislocations anymore, but we do see grains. And the microstructure is the grain size, shape, and orientation distribution of the alloy. And these distribution functions will have an influence in the mechanical response. And we can even go farther, and we can go to a length scale where we do not see the grains. We see a continuum of more or less anisotropic matrix, but we see some large second phases of reinforcement particles that can be a normal metal or a particle reinforced composite, okay, and in this case, the shapes, volume fraction, and sizes of this particle might affect also the mechanical response. Okay, so in addition to the effect of the microstructure in terms of topology, there is an effect that is a size effect. This means that even for the same topology of the microstructure, let's say grain size distribution or volume fraction of reinforcement particles, the actual size of the microstructure has an influence, okay, in the mechanical response. This is what we are interested in. This is what I will present. When does it happen? So at the micro scale, this is something very common that we found, that is something that we call the Hall-Petch effect. So we have the same grain size distribution for the same heat treatment, same material. Here, an example is Zinc 780. And just the variation of the average grain size produced different behaviors. So this, in this case, the smaller the grain, the stronger the response. In a larger length scale, when we have, let's say, particles or inclusions embedded in a metal, okay, so for the same volume fraction of particles, we can have an effect on the actual size of the particle. So in this case, the smaller the reinforcement particle, the stronger the response. And this effect is also observed in ductility. Ductility is also affected by the size of the particles. Okay, so we want to study that, and we want models that are able to link this microstructure, including size effect, with a macroscopic response, and computational homogenization is probably the best option. So computational homogenization just aims at obtaining the macroscopic response and solving also the microfields, as been shown by Dirk in the previous presentation, by solving the boundary value problem on an RV of the microstructure. In this case, the results depend on the microstructure and the behavior of the phases. That can be anything from elasticity to crystal plasticity or damage models. And in order to conceal these two aspects of size effects and computational homogenization, we have two main challenges. The first one is that we have to develop or to include size-dependent constitutive equation or approaches if we want to capture size effects. And standard crystal plasticity or standard plasticity or some fracture approaches do not consider size-dependent behavior. And the second one is if we want to take into account the effect of the microstructure accurately, we need to use large RVs, very complex, that represent accurately the microstructure. So these challenges have been, of course, studied in the literature. From the first one, there are a lot of models that are that introduce size dependency. So in the case of the microscale, we have strain gradients in the crystal plasticity, micromorphic models, mid-frequent models. In the case of the mesoscale, we have other similar approaches, but normally these models are very complex and are applied under simplistic approaches and have only been applied so it's difficult to find this complex model applied in complex three-dimensional simulations. Okay, respect the second challenge, okay, that is using large RVs. So the problem is very much related. So we have alternative approaches to FEM, like FFT, that is the basis of Damasc, for example. But many times, okay, these models use standard models, although linked with other chemo or temperature-dependent constitutive or let's say problems. The mechanical equations are very often local, so standard. And so the threat is just to link the two challenges, and this is precisely the objective of this review work. So we want to develop a microstructure-dependent models based on FFT homogenization that allow us to study and predict microstructure size effect. I just emphasize what means microstructure size effect. So gradient models appear when the community wanted to see why having a different and specimen of a different size, they obtain a different response. So here the size effect is the relation between the specimen length or some characteristic length of the specimen respects some intrinsic length of the material. In this case, we're speaking another type of size effect. We're studying material size effect, and in this case, the relation or the size effect comes from the relation between some characteristic length of the microstructure, not of the specimen, for example, grain size, particle size, distance between particles, things like that, with some intrinsic length scale of the material. Okay, and in this case, we will present two works. One is on the microscale, where we will study through a strain gradient crystal plasticity model, the grain size effect, and another one is on the mesoscale, where combining strain gradient crystal plasticity with an implicit gradient damaging approach, we will study the effect of particle size in particle reinforced composite. Okay, which is the common framework, the common homogenization framework? Well, the common homogenization framework is FFT homogenization, and FFT homogenization is not new at all. It's almost 30 years old. Okay, it was introduced by the pioneer work of Moulinex and Souquet. What is the key idea? I'm not going into many details, but the thing is, we have discrete fields, and we can operate with these fields in the Fourier space. So we transform into the Fourier space with a discrete Fourier transform, and then we can perform some operations very efficiently. The first one is that a field can be derived just as a multiplication. So the Fourier transform of the derivative of a function is nothing but the product of the frequency by the transform of this function. Okay, so by a product, we have the operation of derivative. And it's clear that using this and combining this in several dimensions, we can obtain expressions for different differential operators like divergence, gradient, curl, and so on. And the second thing, it's the convolution. So if we use Green's function, the solution of a problem can be obtained as a convolution of the Green's function with some source term. And this is the basis of the Fourier method. And the problem of this is that in the real space is extremely expensive because we have an order n square operation. But this convolution operation can be performed almost not for free, but very, very cheap in the Fourier space, because the convolution is just a product. Okay, so with these two ingredients, boundary value problems and heterogeneous RBE, okay, can be used very easily. And the key is that this transformation from real to Fourier space can be done very efficiently. So operations in Fourier space are fast, but also moving fields from real to Fourier space is very fast because we will make use of the FFT algorithm. That is an algorithm that allows us to do the transformation in an order n log n. Okay, so what do we decide to do, and what are the benefits then? So there are three main benefits of FFT solvers for computational homogenization, and I emphasize computational homogenization, not for general boundary value problems, because the things become much more difficult and tricky in that case. Okay, so in the case of computational homogenization, the three advantages of FFT respect FEM is first the periodicity, that is something that is ideal in the case of computational homogenization. This is something natural in FFT. On the contrary, on FEM, it's something that introduces an additional complexity and an additional computational cost. The second thing, it's the computational cost itself, that the most expensive operation in FFT is the Fourier transform and is order n log n. While in FEM, depending on the solver, if we have direct solver or we have an implicit solver, and depending on the bandwidth, we are normally in order n square n cube in the computational cost. So it means that we can reach with the same time much larger RBEs or doing more statistics. And the third and very important thing that has also been shown in many examples by Dirk is that we don't need to mesh. So we can use directly information from tomography or from EBSDs and do a direct simulation. So we decide to build our own FFT code that is more humble, of course, than Damask. And the reason is that we want to have something more general, not just devoted to crystal plasticity, and that we can modify by ourselves. So this is a project that started only 4 years ago, and we developed a code that is called FFT-MAD. Okay, that is, let's say, a generalized, a general homogenization code, so not for metals, but for in general computational homogenization. So in the code, we implement several FFT schemes beyond the ones proposed by Moulinex and Souquet, that are polarization schemes. We have our own displacement-based scheme instead of the strains. We have Fourier-Galerkin schemes. The second thing, we want to be totally general. So what we did is we include constitutive equations using an abacus unit. So in this case, we can use our FFT code with any other UMAT defined for finite elements without doing any change. So we have a wrapper and we have a UMAT for, I don't know, viscoelasticity, and we can use it directly in our code. So the code, of course, is efficient. Because this is the main thing of the homogenization. We have parallelization in multiple cores, and we have some modules that are also parallelized in GPUs, okay? And the fourth thing is that we have been working now more than 4 years in the code, and we have include models at different nanoscales. So in the case of the nanoscale, we have explicit representation of dislocations for interacting with Monte Carlo models, being kind of a dislocation dynamic approach to move dislocations and to obtain fields of dislocations within simulations. We have microscale approaches, crystal plasticity, strong gradient crystal plasticity, mesoscale approaches, standard constitutive equation, phase field fracture, damage, and so on. And just to finish, just about the computational cost, this is a study that we did 2 years ago, comparing abacus for the same microstructure, same constitutive equation, okay, and different RBE sizes, and using in abacus the best or the most efficient possibility is using iterative solver, indeed the same iterative solver that we're using within FFT. And we see that when we go to RBE sizes of 128 voxels to the cube, that is around 2 billion of points, we are 5 times faster for exactly same RBI, same constitutive equation, and so on. But when we move to 60 millions of voxels, that is 256 to the cube, then in FEM we cannot even allocate a problem for the same computer. Okay, so what is the computational homogenization problem? So the statement is we have an RBE, and this is a real RBE that we have solved within FFT with thousands, I think it's something like 20,000 grams, okay? And we want to solve the equilibrium, divergence of Piola-Kirchhoff stress equal to 0, okay? We want to solve the equilibrated stress, okay, under some boundary condition. Which are these boundary conditions? We impose the macroscopic deformation gradient history, and we impose combine or mix boundary conditions. So in some directions, we can only know, we can also know the average stress. So in this case, what we want to solve is the mechanical problem of the equilibrium under some macroscopic stress strain and having the fields being periodic, okay? And how we couple that with higher order models, we do it using a staggered approach. We solve this problem, and then we solve for the enhanced higher order problem for the couple equations, and we do it until we get convergence. So in terms of the Fourier of the Fourier solver, we are now focusing many times on Fourier-Galerkin approach developed by Jan Thielman, Bondrech, and co-workers and some others that we have combined with our own method to impose mixed boundary condition. So we do not have to iterate for obtaining uniaxial stress, but we can directly impose free stress or some given stress in some directions within the product. Okay, so I'm going to pass over this. It's not in the scope of the talk, but this is what we are using. Okay, and then let's go to the two problems that I want to show. The first one, as I told you, is on the microscale, and we're interested in using this technique to obtain grain size effects in polycrystals. So the grain size effect is very, very old problem and very well known, and there is a very well known relation that is written here. That is the Hall-Petch relation that tells us that the flow and the yield is related with the inverse of the square of the grain diameter. And this law is a good scale experimentally, not exact, because this exponent is not exactly 0.5 and some other things, but it works more or less properly for many, many works, for many, many material. But we have an interest, so first of, okay, so understanding which is the origin of Hall-Petch. knowing if it's universal or it depends on other factors or microstructure items and so on. So in this case, just combining strain gradient crystal plasticity with computational homogenization through FFT can help us to understand and to answer some of these questions. Okay, first, which is the physical origin of grain size effect? So it depends very much on the particular alloy, but one of the most common mechanisms that give rise to size effects is the accumulation of geometrically necessary dislocation around grain boundaries. Okay, and this geometrically necessary dislocation appears due to the plastic incompatibility and the accumulation of dislocation pileups near grain boundaries. Let's explain this. So when I have a grain that wants to be formed in one direction, another in the other direction, because crystal plasticity is very anisotropic, what I have is some strains, okay, that are not homogeneous within the grain, okay? These strains have a variation from the grain boundary to the interior. In order to accommodate this gradient of the plastic strain, we need to put into the material some dislocations of the same sign that somehow cover this incompatibility in the deformation, okay? These are what we call GNDs and are the responsible of that. Of course, for the same change in plastic strain, the smaller the grain, the larger the gradient, and then the larger the amount of GNDs that we have to put there. And this is where size effect, this is one of the sources of size effect and the one that we are considering here. But nevertheless, this size effect depends on many other factors. So the anisotropy of the crystal, the particular texture, the initial dislocation density. So we cannot use any universal equation. Let's say that Hall-Petch works good or bad because we won't fit something very simple into a very complex problem. Okay, so what is the approach that we want to do? Is let's instead of using this equation, let's do a virtual test. Let's put the microstructure, as much information as we want, and let's then make a virtual test, okay, just changing the average grain size and see which is the size effect that we get. Okay, for this we need a crystal plasticity model. I will go fast. So the model has the standard kinematics of multiplicative decomposition. Plastic velocity gradient is the Schmidt factor multiplied by some shear rates, and the driving force is the resolved shear stress tau, that is nothing but the projection of the stress in the Schmidt through the Schmidt tensor. So the shear rate here follows a phenomenological power law, okay, which the driving force is the resolved shear stress, and we use simple, because we want to limit very much the number of parameters, a very simple physically based model. The model is based on Cox-Makin, so we have an internal variable that is the statistically stored dislocation density. We put just here rho, and we see that we say that the evolution of the dislocation density is driven by the Cox-Makin equation, which we have a creation or accumulation and an annihilation term. Okay, we have some parameters, so the availability of the material to accumulate dislocations, that is somehow modeled by K, and another that is the distance from annihilation. Okay, so good, this is the evolution of this internal variable, and then the critical resolved shear stress is directly given by the Taylor model, where we say that the critical resolved shear stress is nothing but the shear modulus, the Burgers vector, and the sum of the dislocation densities pre-multiplied by some factors that account for the different junctions. So the different type of latent hardening of some systems to the other. Okay, so what we are doing is, instead of using like in the original Cox-Makin law, full dislocation density, we're splitting it in statistically stored and generalized, and geometrically necessary dislocation. The statistically stored follow this equation, okay? But the GNDs is something that evolves through a kinematic restriction, as I told you. That is, they have to be there because they have to somehow take the gradient in the plastic in the plastic deformation. So how we measure this density of GNDs? So Nye proposed a tensor that is an I tensor that relates the density of GNDs, okay, and it's a second order tensor. So it's something like a tensor that is given us the curvatures, okay, because the curvature is what we relate with the density of GNDs. From the macroscopic viewpoint, the Nye tensor, as I told you, is a generalized curvature, so it can be obtained as a curl of the deformation of the plastic deformation gradient. So we have these two expressions, and then we can get the density of GNDs, okay, obtained from the curve of FP. How we do that? We do a minimization. So we want to find the dislocation density of GNDs in each of the systems that we consider, 12 in the case of FCC, that minimizes, okay, the number of dislocation, because this is 9 components and density of GNDs is 12. So they are infinite solution of GND density that give me the same 9. So with this minimization procedure proposed by Arsène Lys and Parks, we can get a direct relation. So we do that, and how we solve this? So because we are in FFT, we can very easily do the differentiation, the curl operation in FFT, because we know the internal variables exactly at the same points where we know the other fields. So we just do the curl, and we take care that we don't have some noise, because we have a FP that has some strong discontinuities from grain to grain. Okay, I'm not going into the details, and we apply that, and we show how we can obtain size effects. So we're going to use 4 alloys: copper, aluminum, nickel, and silver, okay, and we're going to use this type of RVEs with 100, 200 grains and different discretizations. The model is not cheap, so we normally use 100, that is enough. Okay, we're going to create a synthetic RVI with an average grain size and standard deviation following a log normal distribution, and we're going to use for this example just a random texture. So now the model has some input parameters that are obtained from DD in the case of some dislocation interaction or from experimental studies, but we have not fit any parameter. That's precisely the reason why we want to minimize the number of parameters of the model. And then we can see in this model, which is the effect of initial dislocation and average grain size. So from left to right, we have different initial dislocation density, 10 to the 12, 10 to the 13, 10 to the 14. These are stress strain curve. This is only for copper. And in the curves, we have the stress strain behavior for a very large grain size. This is infinity when size effects are not present, and different grain sizes from 80 microns to 10 microns. Okay, we obtain the, as it is expected, the typical grain size effect of smaller is stronger. We see first one very interesting item, that the larger the initial dislocation density, the smaller the size effect that we have. Why? Because we collapse the Cox-Mecking law much earlier when we have a larger initial dislocation density. Where do the GNDs go? They go to the grain boundaries. That's where we have the largest gradients. That's where they accumulate. And since they accumulate there, the dislocation cannot grow more, but we have stronger points near grain boundaries. Okay, and with this model, can we reproduce laws from experiments? So we have compared with a set of experiments by different people in different material. Now I'm showing only copper and aluminum, and we are checking our simulations for the yield, so very low strain and large strain, and we see that we're able to predict size effect very accurately for the yield or for near the yield, okay, but we sometimes, depending on the metal, especially in copper, not too much in aluminum, overestimate the size effect, okay, at larger strain. So in the case of 5%, so it's the flow. Okay, so this is due to the way we incorporate the gradients through the GNDs in the Taylor model. then we can say that this is something that we want to improve, but I want to emphasize, and that's why we're quite happy with this model. It's published in the JMPS in 2020, that the interesting thing is with a quite simplistic model, we're able to reproduce experiment without fitting parameters for many FFC alloys with quite good accuracy, considering more or less the physics of the problem. Let's go then to the next problem, that is size effect at the mesoscale. And in this case, we're going to focus on particle reinforced composite. If we don't have the effect of the grains and we consider that the material, it's like a monolithic material, isotropic or anisotropic, but what we observe in the microstructure are particles, we have a particle size effect. So it means that from the same volume fraction, okay, we have it here, okay, on the left and on the right, for the same volume fraction, we can have different response if we put different particle sizes, okay? And the type of size effect is the smaller the particle, the stronger the response, but we also have an effect in ductility. And this effect is not so clear, but it depends on the dominant damage micromechanism. So if we have interface the cohesion, the smaller particles produce a more brittle behavior, but if everything is ruled by matrix damage, that's what we're going to study, and this might happen at high temperature, then the smaller the particles, the more ductile the material. And what's the physics behind? And what models do we have if we want to account for this? In the case of ductility, okay, we have to think in the intrinsic length scale. And this intrinsic length scale, that in the case of the smaller length scale was the Burger's vector, in this case is the size of the damage band. So in ductile failure, we observe a band of damage. So we don't have a located crack. We have like a damage band, okay, that introduce an intrinsic characteristic length. And then the ratio between the characteristic band of the damage with the size of the particles is the one that drives the size effect in terms of fracture. And in the case of a strength, okay, let's say the reason is more or less the same than before. So there is some characteristic, intrinsic characteristic length scale that is the one equivalent to the Burger's vector, okay, but it depends on the model that you take, but it's the intrinsic characteristic length of the plasticity, and then the size of the particle respect the characteristic length introduce the size effect. So in this second case, when the particle size is much larger than the characteristic length for the plasticity, these effects are negligible. So what is the objective? We want to develop an FFT framework to study particle size effect in particle reinforced composite, including ductility and strength. So this work has been published in Computer Methods and Applied Mechanics in terms of the model, and it's and the one of size effect is now under review. Okay, so let's start then with the damage model. How we study damage? So we can use phase field fracture as proposed by Dirk Rabe in the previous equation, but we prefer to follow another approach in the case of ductile damage, okay, that are continuum ductile damage models. There are many continuum ductile damage models, and some of them are mechanism-based, others are more thermodynamically but phenomenologically based, and one of the most famous one is the Gerson-Vegard-Middleman model. Okay, in this case, we construct a constitutive equation that mimics the damage micromechanism. And the damage micromechanism in ductile metals are the nucleation, growth, and coalescence of small microcavities, okay, that form this damage band that at the end converts into a crack. So in this case, the Gerson model, that's very famous, I'm not going to insist on it, is just a yield or flow surface that introduces a dependency on not only the deviatoric stress, but also on the pressure through some volume fraction of porosity. The volume fraction of porosity evolves, it's like damage variables, and evolves for nucleation and for growth, okay? And then with this model, we are able to predict both the response macroscopically, but also having an idea about which is the level of microscopic damage in terms of volume fraction of voids. The problem of these continuum damage mechanic models, it is very well known for many years, is that when we implement and when we try to solve it, then at the point where we reach the maximum, we reach a condition of instability. So we lost the ellipticity of the governing PDE, and then the deformation starts to localize. Okay, localization is not the problem. The problem is that localization numerically occurs in one element or one voxel, and it's absolutely dependent on the mesh size. So this can be viewed here. So depending on the grid size, the damage bands become smaller and smaller. And the consequence of this is that the energy dissipates in a different amount depending on the mesh size. So instead of having the same or more or less the same behavior for different mesh sizes, we have a strong mesh effect that is pathological, is unphysical, and that we cannot somehow survive with it. How we can solve it? There are different approaches, but we focus on using non-local models. So what is the idea? The idea is that some internal variable that can be the volume fraction of porosity or other variable, okay, does not depend on its own value, so it's not local, but depends on some surrounding points. So we can say that this internal variable, imagine the porosity, the non-local version of it is just the integral of some weighting functions by the value of the local counterpart in a region that is controlled by a characteristic length. This integral non-local model is very hard to be integrated in standard continuum mechanics framework. So what we can do is do a Taylor expansion of the expression and playing around with the equation, converted into a gradient approach. So in this case, the unknown is the non-local internal variable, and this can be obtained by solving this partial differential equation that is the Helmholtz equation. It's nothing but the same equation that we solve on phase field, okay, and we have a characteristic length like in phase field and some boundary condition that are free Neumann boundary condition. What is the difference? Well, the difference here is that the source term, it's the local value of the internal variable. And the other difference is that the characteristic length here, okay, it's a physical parameter. It's not a numerical parameter. This physical parameter, it's related to the size of the band in which we localize damage, okay? So not like in a phase field fracture when we think in linear elastic fracture mechanics where the correct solution is tending L to 0. In this case, L is a parameter that we have to consider because it's part of the physics, okay? So in the case we have to solve a couple system of PDEs, the equilibrium equation in which sigma depends non-linearly on the non-local variable, and the Helmholtz equation that delocalizes the value of the internal variable. Okay, so which internal variables do we delocalize in Gerson? So instead of delocalizing the volume fraction of porosity, we delocalize the volumetric plastic strain, okay, and the equivalent plastic strain. So in this case, the evolution of porosity depends on the non-local counterparts of these internal variables. Okay, good. So we have to solve a Helmholtz equation for each of them. And the second question is how we account for materials where we have non-damaging phases. So in this case, we can introduce a characteristic length that depends on the position. Just a trick, because we're going to make the characteristic length for the points belonging to non-damaging phases tending to 0. If we do that, we have proof that we recover the free Neumann boundary condition, as we will see in the experiment. So with this thing, okay, we have the, sorry, let me go back. So we have the first part that is the gradient model and the damage model, and the other is strain gradient plasticity. So what we're using is the mechanism-based strain gradient plasticity model that is exactly the same as the crystal plasticity counterpart. Okay, so it's based on the Knight tensor through the curl of epsilon p, and it's introduced an expression that emulates Taylor's. Let's say that is the upscaling of the previous constitutive model. So we're now going to see how it works on particle reinforced composites, first in 2D. Okay, and let's first check if we are able to solve the pathological localization problem. And we're plotting here the response of local Gerson and here the response of non-local Gerson, where we have three different voxel sizes. Okay, so the first thing that we see is that the response collapses for the three sizes, so we do not have a pathological size effect anymore. That is the first thing that we want. And if we go to the microfields, we can see very clearly the difference. So in the case of local Gerson, bands become smaller and smaller, but in the case of non-local Gerson, the size of the bands is independent on the voxel dimension, on the discretization. And what we observe here, this let's say thinning of the damaged band is it's due to the fact of the boundary condition between the phases. So we have a free Neumann here. Okay, so because we don't want to introduce damage in the non-damaging parts, okay, then it means that the distribution for the damage is affected through this. This is something that will happen also on phase field damage, and it comes from the free Neumann boundary condition. Okay, let's go to 3D. Three different sizes. Now the RBE is a particle reinforced composite with spherical particles that are randomly locating, 20% of volume fraction, and the same. The original model, local, it has a size dependency, while the non-local model has the same behavior for all the different discretizations. And we are able to model, which is the band, okay, how does the band locates, and we are able also to show how the band evolves. Okay, so we have developed a very, very nice model that allows us to do 3D simulation of fracture or damage in this case, considering complex microstructure. So I have no time almost to finish, just showing that if we combine strain gradient plasticity with damage, we can observe the effect, the size effect. So the first one in damage, it's that the smaller, okay, the particle, the more ductile. We see that the curves move to the right, and in the case of the strength, okay, the smaller is the stronger. And if we combine both, we can see which are the optimal grain sizes, okay, sorry, grain sizes, particle sizes for particle reinforced composites. So how this fits with experiments, in this case, we have a quite phenomenological model, so we have to fit parameters. And what we observe is that if we fit just plasticity without damage, we are not able to predict the response for large strains, okay, but we predict well the particle size effect, okay? And if with this model fit up to here, we just include the damaging part, we are then able to measure the first part where damage is not playing any role, where we have particle size effect, and the second part where the size effect in particle in damage play a fundamental role. Okay, so, well, that's what we have done. And let's say that the main conclusion is that FFT homogenization is a very interesting tool to be combined with any type of non-local approaches through staggered models. I have not shown which is the techniques behind, but it's a good way to predict the effect of microstructure in the mechanical response, but including size effects, both in monotonic response, but including that. And I'm just on time. Sorry for the delay, and that's all. Thanks for your attention. And if you have any questions.
Yeah, thank you very much, Javier. So the talk is open for discussion. Do you have any questions? Yeah, we have two questions. So Lei Louis, yeah. Go ahead.
Hello, Professor Segurado. Can you hear me?
Yes, I can.
Thanks for your nice presentation. I have a short question about your trick about how to account for the non-damaging phase. Can you go back to that slide?
I don't know if I'm sharing right now or not.
Yeah, you share.
Yeah, okay. So which slide you want me to go back?
The slide which you show your trick about how to account for the non-damaging phase.
Okay, good. So LX. Yeah, it's before. Let me here.
Yeah, this one. Yeah. So I'm thinking by you basically I'm thinking about the equation L, the length scale far smaller than the damaging length scale. So why not the other way around? So yeah.
Which is the other way around?
For example, for me, I will think if you make the length scale L much larger than the damaging length scale.
No, well, I don't have it here, so it's proved using taking a volume over two faces, okay, making the integral and posing the continuity of the fields, you end up with a relation in the interface between the two faces. And this relation tells you that if you want to have a free Neumann, so if you want that the damaging phase has an evolution of the internal variable, which gradient multiplied by the normal is equal to 0, can be done if on the other side you have a characteristic length that is much smaller. So I'm not putting here any detail, but this is formally proved. Okay, but from a qualitative viewpoint, you can imagine something like this. So imagine that you have an elastic phase, okay, and you use just the same characteristic length for all the RV. Then, although the internal variable is not defined in the elastic phase, when you make the averaging through the Helmholtz equation, it will diffuse inside, okay? Because the length of the diffusion is controlled by L. If you set the characteristic length in the non-damaging phase to tend to 0, you will not diffuse them inside. That's the thing.
Yeah, I understand now. Thank you.
So there is another question from Yuri Kadin. Yeah.
Hi. First of all, thank you for a very interesting talk. I'm quite impressed. I have a question. It's, I think, quite engineering question. So you use here non-local approach, which is based on material scale parameter, which you call LP, if I'm not mistaken, or LD. So yeah, as I said, a practical question: how to calculate this parameter? Because there are some different approaches. For example, if you follow approach of David Taylor, so he calls it critical distance. It's based on toughness. So
well, yeah, this is a very interesting and hard question. So when you go to the mesoscale and to phenomenological models, then the characteristic length are not well defined. So if you follow the crystal plasticity, sorry, the mechanism-based strain gradient crystal plasticity, you get a measure of the characteristic length, okay, that is somehow based on some dislocation measures, and that scales with the Bruegger's vector. Okay, it's the less phenomenological of the mesoscale models to account for that. But at the end, it just gives an order of magnitude. It does not even give an actual number. So in the case of characteristic length in plasticity, from my viewpoint, it is not easy to obtain that from background, from let's say, from very clear principles, but normally you have to fit it with some macroscopic experiments. This is one thing. And the other one is the damage characteristic length, the size of the band. This is even worse, because in this case, it has been shown that this characteristic length is not even material dependent, because you can find different thickness, different band thickness for the same material under different loading conditions for different triaxialities. So it's convenient to have and to introduce this characteristic length, but it's not like the yield stress or other parameters that are well defined and related to a material. Okay, they are, let's say, controversial parameters that from my viewpoint, from an engineering viewpoint, it can only be obtained by standard physical principles in an order of magnitude. And to be accurate, somehow you have to make tests and obtain them for the particular condition you want to study. Well, this is kind of an opinion, and we have not gone deep into that because we're more focused on the methodology and see how we get it, but this is complicated.
Yeah, I agree. It's very complicated, and yeah, what you mentioned, at different scales, you can have different characteristic lengths. So depending on complexity of material.
So, all right. So there is one more question from Elat Priel. Yeah, please.
Yeah, thank you for a very, very interesting talk. I have one short question. You showed that decreasing the particle size, you can very clearly see the size effect with increasing ductility and increasing strength. But the question is, do you think that if you increase your volume fraction, and when you increase your volume fraction of particles, you may have a change in the damage mechanics, because currently you're only looking at damage in the matrix, and you're not looking, if I understand correctly, on delamination or fracture of the particles. So if you increase your volume fraction of particles, you may have a change in the damage mechanics and obtain different results. Is that true?
Yeah, that's absolutely true. It's a good comment. I told at the beginning that the size effect in strength was clear. Smaller is stronger, but in ductility, it totally depends on the damaging mechanism. And in the case of particle fracture or decohesion, normally the size effect is just the contrary, is what it has been observed experimentally. The smaller smaller particles break earlier or have a decohesion earlier. So if we introduce into the model, that's something that we're going to do in the next future, because we can have delamination using phase field fracture localized on the boundary. That's something that the group of Dirk has also worked on. You can put all the mechanisms into the same model. And in this case, as you suggest, volume fraction will play a role, because for small volume fractions, you can change from one mechanism to other. Small volume fraction might lead probably to just damage on the matrix, and you will get what I have shown. But for larger volume fractions, you promote particle fracture, and then you will get in ductility the other effect. That's absolutely right.
Okay, thank you. Thank you very much.
All right, thanks. I also have one question. In your polycrystalline RV for the gradient model, what type of boundary conditions do you use for the plastic field? For the, I guess you have a GND boundary conditions.
Because it's a lower order model.
Ah, okay, it's a lower order.
It's a lower order model. So the good thing of FFT is that different to finite elements, you evaluate the fields for if you have a displacement-based displacement, otherwise stress is strain at the same point at internal variables. So using the same field operators that you use to obtain the PD, you can also derive the internal variables without making any trick like what you do in FEM. So what we do, in this case, so the problem is lower order, because what we do is to derive, obtain the curve, and plug it into the constitutive equation. In the case of the damage model, we obtain the gradient, but in this case, it's a higher order model. So we solve in parallel two PDs. We have a specific boundary condition for the non-local variables, and we have a staggered, fully implicit approach. Okay, in the case of plasticity, we didn't thought it was necessary, and it simplifies to do it that way, especially in the case where we mix all the models in one.
And one more question. I mean, we are a bit late, but it's good discussion. So in the RVE, the RVE is not periodic, right?
Yes, it's periodic.
I mean, boundary conditions are periodic,
Yes.
but RVE also, the
Yes.
structure is periodic?
Yeah, what we do is a tessellation, having the points not only in the RVE, but also in periodic position. So when you make the tessellation, the point on the left of the RVE will see the same cloud of points that the one on the right. So when you construct a tessellation larger than the RVE and you cut, you get the periodicity. That's something that is very important because I think it's, if you have a periodic boundary condition, you should combine with the periodic geometry, because in this case, you fully get rid of surface effect, okay?
Yeah.
And that's precisely the objective.
Yeah, okay. Thank you very much.